Okay, I think we'd better get started. So I'd like to welcome everybody to the first EPSRC Network Plus in Digitalized Surface Manufacturing webinar, and we intend these to be a regular event. And we're very fortunate to have Professor Richard Fu from Northumbria University to give this first webinar. Professor Fu was a reader in the Thin Film Centre in the University of West of Scotland in Glasgow prior to going to Northumbria. And then prior to that, he was a lecturer at Heriot-Watt University. He obtained his PhD from Nanyang Technological University in Singapore, and then worked as a research fellow in the Singapore-MIT Alliance and a research associate at the University of Cambridge. He's got extensive experience in smart thin films and materials, in biomedical microdevices, in energy materials, lab-on-chip devices, micromechanics, MEMS, nanotechnology in general, sensors and microfluidics. So he's a perfect person to present this webinar. And he's established a worldwide reputation for his pioneering research in shape memory films, piezoelectric thin films, and nanostructured composite films for application in MEMS, and as well as in sensing and renewable energy applications. His research has been funded by organizations such as the EPSRC, the Royal Society, the Royal Academy of Engineering, Innovate UK, the KTN, AWE, EU, and many others. He's published over 350 SCI journal papers, including very many Q1 journals, plus 2 books, 20 book chapters, and over 120 conference papers. So with that short introduction, I'd like to hand over to Richard to present to you this lunchtime. Thanks very much, Richard.
Yeah, thank you, Alan, for introduction. So very nice to be here. It's an honor to talk with my research experience and background. So I'm going to share the screen now. Okay, so the topic which I'm going to present is about the smart thin film designs for sensors, actuator, and lab-on-chip applications. As we know that, so we have different applications using the surface thin film coating and some technologies, which using the different wide applications. And then there are normally have strong requirement for good mechanical property, and some of them are required for very good functional property as well.
Richard, can I just interject? Sorry, Pamela's just reminded me that I need to tell everybody that this is recording live on YouTube. So people need to be aware of that if they want to speak or if they don't want their image to appear or anything like that. So sorry to interrupt. Carry on, Richard, sorry.
Yeah, okay. So, so basically, for the mechanical property, so there is a very strong requirement for the coating or thin film should have both very high hardness and also very good toughness. So for hardness and toughness, normally for coating, it's quite difficult to achieve for both the properties. If we increase the hardness, normally the coating will become quite brittle and the crack easily form and propagation. So there is a very good design for the using the nanostructured thin film, which can achieve both the high toughness and hardness. So this is based on the Hall pitch effect. So if we reduce the crystal size of the coating, and then we can achieve very good hardness, and also the crack propagation will be reduced. So And along with the reduce the grain size, we can achieve a lot of different property of the film. Well, there is also always question that if we continue decrease the grain size, will the Hall pitch effects continue behave? Will continue increase of the hardness or strength? Well, there is the critical point, which is about 10 nanometer or 20 nanometer, depending on materials. And then below this critical size, the material become much softer. We normally call it anti-Hall pitch effect because the grain boundary or become amorphous phases become much dominant. Then the material become much softer through the grain boundary sliding mechanism. So that means if we can prepare the film, which is within the grain size of tens of nanometers, then we can achieve very good hardness. So in order to achieve the high performance of the coating and thin films, there are different designs. So if we simply reduce the size, and then we can achieve hardness, but then the crack easily propagates through the materials, and then the coating still have low toughness. So that's why we're using the different designs, for example, nano-graded films. So the coating from the top surface, gradually changing layer by layer, nano layers of the material, graded changing the different coating, type of coating until to the substrate, which we can increase the crack propagation resistance and also enhance the material load bearing capacity. Or we can using multi-layer nano layer designs. So the crack would not be easily propagate through it, and then increase the energy and then increase toughness. So this is another design. And also there we can using the nanocomposite coating design, which we embedded the nanoparticles within a matrix of the tough substrate. Then we can achieve very good performance. So I will using one example, which is a nanocomposite idea, illustrate how can we design it. So basically here is illustration is that how can we design the nano composite coating, which can have the hardness as hard as near to diamond. So basically the idea is that within a very tough matrix, for example, we're using diamond-like carbon or sometimes silicon nitride as a very tough substrate. We doped with elements, for example, silicon or aluminum to make the substrate matrix much tough. And then within this matrix pattern, then we have a lot of different nanoparticles. So these are maybe for the different carbide or nitride, which is very hard. And then size need to be controlled within about tens of nanometer. And then the distance between each particle should be also very well controlled because we want to let the crack propagation and also increase the propagation path. And also the orientation of the coating or of the particle also need to be controlled. So that means they have different direction of control, the strength and hardness. So how to realize it? So we normally using magnetron sputtering. We use a multi-target. For example, we can using carbon graphite target together with metal target and a few of them within gas mixture of argon or oxygen or nitrogen. So there are a lot of optimization of the parameters. So the process parameter, including power, gas ratio, pressure, can be controlled. And then we can achieve within a kind of matrix pattern, we have a lot of small dots pattern, which is nanoscale. And then because it's nanoscale, the electron diffraction pattern normally is ring pattern, which showing the structure. So we can further using the high magnification transmission electron microscope to observe the coating, optimize the coating. And we can see that there are truly a lot of nano-sized particles with different orientations. And then between the different nanocrystals, there are amorphous states, which is a matrix pattern. And also through the lattice, we can know that there are different carbide or nitride for the different orientations. So this is achieved a very good performance. The aim at the beginning is that we want to get the coating which is as harder or even harder than diamond, because in principle, you can achieve the, through theoretical analysis, you can achieve the coating much harder than diamond. But we have done so much work, we have never reached to the, near to the diamond level yet. But even though we cannot increase the hardness or strength much better significantly, we actually achieve very good coating toughness. So that means the coating can prevent the cracking or prevent the peeling off or quite significantly. So for engineering application like cutting tools, we actually not only required for hardness, we also required for toughness as a very important parameter. So, and then I realized that diamond or diamond-like carbon are actually very good materials for the kind of application. So that's why I have done some work which is using the microwave CVD method to grow diamond or carbon nitride film. So we're actually using the idea which is called a nanocrystalline diamond, which can reduce stress of the film and also increase the toughness of film and also increase adhesion of film. And then I access to the clean room fabrication. So we're using lithography and then make a lot of demonstration of the micro devices using the diamond and also using the diamond-like carbon structure. So, so gradually I moved to the MEMS technology. So, and I think that this is a very interesting area which the thin film and coatings can be applied. So in this talk, I will probably focus on 3 areas. So the first, of course, is the thin film and coatings can integrate with the silicon fabrication technology, and then we can make the microsystem using the so-called smart materials. So for smart materials, normally how to define any material is smart or is intelligent. So we often consider that if there is any external stimulation, for example, environmental changing, or for example, external force or pressure, and then the material will respond to it. So there are 2 different responses. So one is, we call the signal will be changing, for example, optical signal, magnetic signal, or electric signal. And then through the signal changing, we predict what is happening, what is the reason. So these are sensors. And then those smart materials can also responding to the external stimulation through the changing of its shapes or its dimension. And then we can use them for actuation. So these are also very good actuators. So smart materials are very good sensor actuators, which are the microsystem. So there are a lot of different types of the smart materials, for example, piezoelectric materials, chip memory alloy materials, or the many types of the polymer and the nanocomposite materials are smart enough. And even for many materials, which are, they are not categorized as smart materials, for example, silicon, those kind of diamond-like carbon, or even the common materials, they are not easily responding to the external stimulation. But we can using kind of smarter designs, which can realize the smart functions. So here I will show just one example to show that we have been doing a work which is on the using the nanocrystalline silicon film, which is a mixture. It's actually a mixture of amorphous silicon with crystalline silicon. And then we make a device which is a two-layer structure. So there is a top electrode, which is multiple cantilever structure, which is separated with the bottom electrode, which is just a square shape of electrode. So there is space between them. So if we apply the voltage between the top electrode, which is multi-layer cantilever, to the bottom, which is square shape, and then there will be electrostatic force between them, because the so nanocrystalline silicon is conductive doped with phosphorus, and the bottom is metal chromium or high-K materials. And then because electrostatic force, then the cantilever will be pulled in. So when we do the measurement, we found that all the cantilevers will pull in one by one, and then release one by one after we apply the voltage or remove the voltage. And then this look like playing the piano. So the cantilever one by one will touch down and then come back. So what is the principle? So we assume that we are making a device which is called a digital variable RF capacitor. So the capacitor basically made by the top electrode, which is multiple cantilever with different lengths. As we know that if we have the two electrode, top electrode, bottom electrode, there will be electric charge. And then after the voltage increase to a certain point, the top electrode will be pulled in because electrostatic force will increase with voltage. And then it's overcome the stiffness and it will touch to the ground of the bottom electrode. Once it touched, there will be digital jumping of the capacitance because there is touch of the two materials. And then the pull-in voltage required to let the cantilever to pull down, which is a function of different parameters. One of them is the overlapping area. So that means if we increase overlapping area, it will reduce the pull-in voltage. So that means the longest cantilever has the highest overlapping area, which have the lowest voltage. And then if you continue to increase the voltage, the shorter cantilever will be pulled in. Each pull in, then there will be jumping of the capacitance. So that means we can digitally increase the capacitance by the finger touch down one by one. So this is a function which we can realize using the, which is common silicon materials, and then using multiple cantilever designs with different lengths. So these are really looks like a playing piano, finger touching down, up and down. Okay, so for the microsystem, I want to using one of the example, thin film example, which is called chip memory alloy thin film. Chip memory alloy, which is a very good material category as smart materials. So chip memory alloy is a very special material. It's normally very soft at room temperature. You can bend it. And then once you heat it up, the bent shape suddenly change back to the original shape. Some material also have super elasticity. So that means the material is bent significantly, but once you release the force, it will return back to original shape. So chip memory alloy has been widely applied in the industry for quite different applications. For example, space antenna, stents, medical structure, or glasses. So what we are aiming is we want to make using the chip memory alloy for microsystem, for micro operation, microactuator for microsurgery application, or micro assembly in robotics. So what is the reason behind the chip memory effect? Basically, there are just two phases changing with the temperature. So at the room temperature, at low temperature is martensite, which is zigzag twinning structure. It's easily deformed. Once you deformed, it becomes deformed martensite. But once you heat it up, it automatically phase transformed into austenite. Austenite just as the same shape as before the deformation. Once you release lower temperature, it return back to the lower temperature phase, martensite. Then the material just doing the twinning inside the material without changing the shape too much. So this is the principle for chip memory alloy. So it's the fundamentally is corresponding to the temperature. So why we need to use shape memory alloy for actuator? So shape memory alloy has very good advantage. So if we have the same weight of material or same volume of the material, the shape memory alloy can produce the highest power or highest the energy, which can do in the actuation. So it's very high power. And also the deformation of the shape memory is significant. So that means it can realize a very large displacement. So these are actually the good advantage for actuator application. So, and also corresponding to the shape memory effect, there are a lot of different signals changing. For example, physical property, mechanical property, and electrical property also changing. Surface pattern property will changing. So that means we can using it for sensors as well. Another advantage for shape memory alloy is that it's actually very good biomaterials, and the temperature, operation temperature can be adjusted even to lower to down to body temperature. So that means we can use it into the human body. So one problem for MEMS application is that shape memory alloy actuation is based on thermal effect. So we need using temperature heating up and cooling down. For all the thermal related to microactuator, the problem is the frequency, because you're heating up very fast, but the cooling down is very slow. So that means the cycling is very difficult. So compared to other materials, we need to increase the frequency. So one way to realize it is that we can using the thin film structure. So we only have a few micron, which is easily to heat up and cooling down. And also we can using the MEMS design. We're using microdevices. We make it a much smaller scale. So that means heating, cooling is much faster. So it's a scaling effect. Of course, shape memory alloy thin film is actually very easy to be obtained. So we're just using sputtering method to deposit the titanium nickel to control the composition, which is 50 titanium, 50 nickel. And because it's a metallic film, the film is actually very ductile if your deposition condition is very good. And then it can be peel off from the substrate totally. And then after peel off, then the material, the freestanding material has the gradient stress in the film, because during the deposition, there will be gradient changing of the composition of the film from bottom and top. So the film will be curl up after you release from substrate. Well, if you're heating up, there will be shape memory effect, which is causing the shape to return to the high temperature deposition shape, which is flat. So that means the material itself, after deposition, it will have two-way shape memory effect. Once it's cooling down, it's curl up. Heat up, it becomes flat. So that means you can using this one as an actuator itself. So that means we can using lithography method to design different structure to realize the microactuator design. For example, we can using this one as a cage structure, which actuated by electric current. Or we can realize the mirror structure or valve structure, which just using the shape memory electric current flow through it, heating up. So we can using the different MEMS design to make the different structure to realize the different functions. But the problem is for thin film is that it's only like 1 micron or a few micron thick. And then this thickness is has very low stress or strength to actuate the structure. So that means freestanding film is actually, unless it's very tiny micron nanoscale, otherwise it's very difficult to actuate a very large scale function. So then in that case, we need to design using the bilayer structure or bimorph structure. So that means we can using the structure of silicon or other structure like metallic materials to make the two-layer structure. So in this way that we deposit the film and then we pattern the film, titanium nickel film into electrode. So on the structure of silicon or other structure, silicon carbide or other materials. So these are two-layer structure. So once you let an electric current flow through this electrode, there will be heating effect. The shape memory effect will changing the shape of the material. So once you release, once you stop the electric current, then there will be a phase transformation, return back to mass side. Then the material will return back because the silicon will bend it back. So that means with a very small low temperature changing, we have the large significant increase or changing of the shape of the cantilever. So this is the bimorph or bilayer design structure. The frequency can go up to hundreds of hertz, which is quite useful for some applications. So if we can design the two cantilever, make them together, then we can realize the function of micro gripper. So the advantage for titanium nickel is it has very large force and also very large displacement. So that means we can open, close with very large force and displacement. So for this application, we can use it for like a gripper or for pickup biological cells or for the robotics operation. So if we're using it for the tissue or biological cells, the trouble is that the tip, because the force could be very large, it's easily to crash the cells. So that means this design, we need to be careful because it might be not applicable to pick up the cell and manipulate the cell. So for this application, we were thinking that, okay, we can have some other structure, which is we're using a few of the finger structure. So we form a kind of cage structure. So this cage structure basically is multi-finger, which is we're using the two-layer design. So this two-layer, we're using the titanium nickel with shape memory on the top of the layer structure. And the bottom, we're using diamond-like carbon. So the reason why we're using diamond-like carbon is because diamond-like carbon has very large stress. So once we release the substrate from the silicon, the large stress will bend the cantilever structure significantly. So it forms the cage shape. So if we let the current flow through these fingers, it will cause a shape memory effect. It becomes flat. So it will open up significantly to open up and pick up things. So we can design the different structure and then form the two-layer titanium nickel and the diamond-like carbon. And then for our operation, the temperature is still a little bit high because we want the operation temperature as low as possible. For example, at room temperature. For this case, what we can do is that we can using integrated polymer inside. As we know that if we have the polymer integrated with this kind of multiple layer structure, then the polymer has very large thermal expansion coefficient. It will bend significantly of structure, and also it has very different Young's modulus compared to other film. So that means if we combine the three-layer structure, it will function much better. Well, when we do the demonstration of operation, we actually pick up polymer ball. So this is like a 40 micron or 50 micron polymer ball. So when in the scanning electron microscope, we can observe its very rough surface. So we just painted the color. So it looks like Earth. So we claim that this photo is given name is Saving Our Planet Earth. So it's for environmental demonstration. Okay, so that is just a demonstration using the shape memory alloy thin film for MEMS application. Well, another application which I want to demonstrate that there is a piezoelectric thin film which can be using for the lab on chip application. So for lab on chip, as we know that we want to replace the hospital operation using tubes. So we propose that the small chip can using very small amount of the biological stuff like blood sample. We separate them into dilute and separate into many small droplets, and then using the technology to move the droplet to different locations and mixed and enhance the bioreaction, and then finally doing the biosensing. So lab on chip have the function of biosampling and biosensing. So there are different technology for realize the lab on chip. So that's why it's very complicated. The chip is small, but the operation or the equipment which quite a lot. So one question always, is there one technology which can realize all the functions from the microfluidics, biosampling to the sensing? So we think there is one technology which is called surface Coulomb wave. So basically this is based on the piezoelectric effect. So for many of the material which is has the tetragonal structure, and then this structure have the special property, once you apply the force, the element will jump into different positions, there will be dipole form, then there is a voltage. And then if you press them, if you apply the voltage, then the element will be jumping and then causing the deformation of materials. So it's actually very good sensor and actuator. So the common materials, including lithium niobate, quartz, zinc oxide, and PZT. Surface Coulomb wave basically is the idea is that on the piezoelectric substrate, if you apply, if you deposit the electrode, which is comb drive structure, and like finger structure, because the piezoelectric effect, if you apply the resonant RF signal, it will generate a mechanical vibration. So this looks like a nanoscale earthquake. So there is a waves generated, propagation on the surface. So this is the reason why we can use it for microfluidics and sensing application. For sensing, it's actually the surface Coulomb wave sensor is actually a very common device. I think most mobile phone has a Coulomb wave device for signal pickup. For surface Coulomb wave sensor, so basically you can using the different designs. One of the design is two electrode design. So you have the electrode that generates the wave propagation on the surface, then go into another electrode to measure what is the frequency. So if anything between the two electrodes happening, the frequency will become different. So you can monitor frequency shift and then predict what's happening. So we can use it for different sensing applications. Well, for biosensing, there is a problem is that if there are too many factors influence the signal changing, then what is real reason? Whether it's because the biomolecular absorption or because DNA structure. So this is actually the most fundamental trouble for most of sensors, the selectivity and sensitivity. How to solve it? We actually design using the lab on chip structure. We make tons of different sensors at the same time. And then each one will be using for different purpose. For example, one is reference to get rid of the substrate, environmental influence, temperature, humidity. Then you can deposit other sensors with different molecules. So that means they are in charge to measure the different signals. And finally, we can using the big data or artificial intelligence method to differentiate what is signal from different sensors and pick up what is real reason. And then advantage for surface Coulomb wave sensor is remote control, is wireless. So that means you can wireless sending the signal to the device and wireless sending out the final results. So there is actually a company in Newcastle proposed using the device. So basically, this is cartridge. You put a sample like a blood sample into it, and then the flow inside for reaction. So after the reaction, there is sensing signal changing. So this signal will send out from antenna to the mobile phone or to the hospital. So this is actually become commercialized. Well, the question here is that there are so many piezoelectric materials, people using quartz for sensor, lithium niobate for acoustic fluidics. Why we need to use thin film or coatings? Of course, if you think about the integration of microelectronics, so the thin film is actually has a very advantage. And if you can consider about substrate, so we can use thin film to deposit on different substrate. We can deposit on silicon for microelectronics integration processes, or we can deposit on glass because the biological people always commonly use glass. We can deposit on some flexible substrate, which I will talk about more later. Then we can have the flexible devices. So another advantage for thin film and coating design is integration. So for bulk ceramics, piezoelectric materials, it's difficult for integration unless you do bonding. But if we're using thin film, we can integrate the process during the IC fabrication or MEMS fabrication. And also, apart from this, we can integrate with different other functions like photonics, phononics, or source, Raman, or different function into the platform. So the idea behind it is that surface cooled wave, the electrode is far away from the detection or actuation area. So we can imagine that this surface cooled wave is actually the football stadium. So all the acoustic wave ID electrode is at the audience, is surrounding. So the inside the field is actually how can we integrate with other functions, for example, photonics, phononics, or Raman, or magnetic. So that means we can use remote controlled SAW as the energy to do both the actuation and sensing. So let me just give some examples what can thin film piezoelectric do with the lab on chip. So the first is that we deposit thin film on it. We put the liquid on path of the SAW propagation. So if you put the liquid in front of the wave propagation, and then the wave, the energy will dissipate into the liquid. So the energy will dissipate into liquid based on the Rayleigh angle, which is the velocity in liquid, velocity in solid, and arc sine coefficient function. And then we can imagine that if we have the energy increased, then the energy, wave energy into the liquid will push up the liquid, and then they're causing the internal flowing, which we call the streaming. So this is actually a very good application for mixing or bioreaction. So if we treat the surface with the hydrophobic, and then if we continue to increase the power, so the droplet is just not only internal streaming, it can be pushed up and flow away. So there is a function of sliding and rolling. So if the higher power, then the droplet doesn't have a chance for rolling, then it's mostly sliding. So that means we can realize the function of mixing. So we can push the small droplet with the blood sample and wash it, dilute it. And then we can also separate it using the surface cooled acoustic device. So if the power increases further, what's happening? So if the power increases further, then there is no chance for liquid to sliding on surface. So the whole liquid droplet will be ejection from surface according to the Rayleigh angle. So this is a very good phenomenon. People think that, oh, we can use it for jetting, for printing. But for printing, people always using the vertical jetting, right? Not Rayleigh angle. Rayleigh angle is quite an awkward angle. So how to realize? So we have different function. We can using circular IDT, which I will not show here, which is concentrate the energy to it. Here we have an example, not circular, but two IDT from both sides. So the energy will propagate from both sides, dissipate into it, push the droplet up. So the wave energy reflected by the interface of the liquid and then reflected and then push up again and again until the whole droplet, the surface tension couldn't hold up the elongation and then break up in small droplet, which is good for printing or purpose. Another phenomenon related to the surface Hughes wave thin film device, which is called nebulisation or atomization. So in this case, the surface is hydrophilic. It won't move quickly, move away, but it stays there. But there is significantly wave agitation on the surface. It's called capillary wave. Then if the amplitude increases too much, then there will be very, very tiny droplet push up ejected. So it forms the kind of mist. So this mist is actually can be used for the nanoparticle synthesis or even for the cell collection, because you can using the glass slides quickly move on top of this mist and pick up a layer of nanoparticles or biological cells. People also using for drug inhaler application. So here is a video showing that in front of the SAW device, we have the droplet, which is a few microliter. So you can looks like the droplet looks like a volcano erupted, and then there will be a lot of kind of nano-sized particle droplet particle will be ejected. So if you continue provide the liquid, then you will have the continued release of this kind of biological information. So another good example is for the cell separation or manipulation. So basically, in this way, we are using an idea which is standing wave. So if you have one IDT electrode, the wave propagation from one side is called propagation wave. If you have the two IDT, two electrodes from both sides, if they have the same amplitude, the same power, same frequency, you will form a standing wave. So once the standing wave formed, then the particle within the liquid will be enhanced the different experience of the forces. And the acoustic radiation force will push up the liquid to the lower energy point, which is the node's position. So that means we can manipulate the particles to the node position. And also, if the particle have different property, for example, sizes are different or density are different, then the radiation force to the particle are different. For example, larger particle have much larger radiation force. They will be moved much faster within the liquid. Smaller particle will be much slower. So we can somehow separate them just by using the time difference. So here is an example. We have very wide microchannel. We have the uniform, very 5 micron particles. If we apply the standing wave, they will form the different lines. So of course, if you shrinkage the width of the microchannel, you can form one line or two lines. So the idea behind it is that we can using this one for cell manipulation or separation purpose. So we align all these particles using the first electrode pair, and then we can using another pair of electrodes to control it, and then to push the different size of particle, different position. And another application is that we can using the SAW device. In this case, we're using the square shape of electrode. Then because it's square shape, then there will be matrix of the pattern of the lower energy and higher energy. So there will be nodes which is formed like the crystal structure. So the application for this function is that we can using for tissue engineering or cell growth or drug analysis. So in principle is that we generate this kind of pattern. We make this, for example, drugs and also cells together, and then we can quickly analyze what's the interaction. Or we can put the cells here and encourage them to growth. So people using it for cell growth or for tissue growth or for hair. human hair growth for different applications. So we also did work using the kind of pram to observe. And then if we increase the height of channel very large, we can realize a 3D patterning of the dots pattern, which is similar to the crystal pattern. For recent work, we are actually doing the flexible device, wearable device. So we're actually using the, we want to demonstrate that SAW device can be used for wearable applications. So for wearable application, people always think the first is polymer structure. So polymer is very soft and bendable. And then if we deposit film, we can make the electrode and then we make a SAW device. But polymer is soft and also the energy dissipated too much. Then the wave doesn't propagation too long. So for microfluidics function, it does not work very well. Then we found another flexible substrate, which is aluminum foil or kitchen foil. So this foil is very thin and flexible and stretchable and easily deformable. So you can easily fix the shape. So we deposit thin film on it and then we patterning it. Then we can realize the microfluidic function. It's bending significantly. The signals are still very good. For wearable applications, then there is a trouble is that when our body or hand move in different directions, we need to make sure that at whatever direction, the droplet still can be actuated, but still stick there very well. So the super hydrophobic design are not good for this application because it's easily falling down if you don't drive it efficiently. So it's actually aluminum surface is very rough, which is microscale roughness. The thin film zinc oxide or piezoelectric material is nanoscale roughness. And then if we deposit a layer of hydrophobic layer, we can realize a surface which is slippery and sticky surface, which is very best application for this kind of wearable application. So we actually deposit the film and make a device on aluminum foil, and then we can demonstrate that whatever the angle, we can pumping it easily. And then this kind of device is also bendable. So that means you can bend in different shape, even there is crack, you still can manage to let the liquid flow to the different directions. So that means in the thin film design, we can realize the lab-on chip all the function using the piezoelectric thin film. So there are a lot of research work going on here. So I will quickly cover the nano application. So I've done a lot of work on the hydrothermal method to grow the nanoparticle or thin film structures, but that is not, that is for different application for gas sensing, solar cells, electrodes, catalyst. But I want to show here is that for people doing the thin film or coatings, can we generate this kind of different shape of nanostructure by using the sputtering or evaporation? So this is normally called the glancing angle deposition method. So the idea behind it that if we put the source and target vertically, then the film is vertically grows in most cases. If you're tilting the substrate, you can grow the inclined angled film. So if you further tilting, you gradually find there is actually spaces between them. It becomes porous. Of course, people using the tilting return back and forward, and then they got a zigzag. So we grow this film for like piezoelectric and surface cooled wave application to generate shear waves. So if you tilting significantly, for example, above 50, 60 degrees, and then there will be nanostructure formed because of shadow effect. So there will be shadow behind it, you couldn't deposit any film. So that means you can deposit the film, which is porous and nanostructure. So if you deposit not only inclined angle, but also rotating, you will got the like a spiral pattern. So this spiral pattern can be controlled precisely because you can control the angle, you can control the rotation speed, you can control the different functions. Then you realize different distance or diameter. So we actually grow the zinc oxide film and titanium oxide film using this method. So these are spiral pattern of the titanium oxide. So these are very good for optical application and also for gas sensor, for catalyst for these applications. So if you further analyze using TEM to analyze the structure, you can see that not only spiral, so each spiral is actually combined by a lot of nanoparticles. So the surface area is huge, which is very good for catalyst and for sensor applications. So I think the time is quite long, so I will stop here. So if we're using the smart thin film and coatings, we can realize the different application for microsurgery, microactuator, and also for lab-on-chip application, and also for energy or for different application. So thank you very much for attention, and also thank all the collaborators and the funding support. Thank you, Alan.
Great, thanks very much, Richard. That was really fascinating. I think we've got the possibility to have questions. Does anybody have any questions at all? I'm not sure if we're unmuted. Pamela, can you unmute people?
Yeah, I'm trying.
So I think people should be able to unmute themselves at this point, hopefully. Any success, Pamela?
No, I can't unmute. I think people have to unmute themselves.
Okay. Nick looks like he's wanting. Nick, were you going to say something then, Nick? Do you want to try unmuting yourself?
Can I ask one question?
Okay, good. Yeah.
Hi, Richard. How are you? Nice to see you. Richard, I think you're on mute.
Okay, yeah, now I'm back.
Very nice presentation. Thank you very much. So I have a question, like if you're depositing films on a surface, what I want to do is to quantify that what portion of the surface has been deposited. So from your vast experience, do you think this is something can be quantified? For example, you've got a 10 millimeter by 10 millimeter surface area. And you are depositing. As you deposit, is there any way through sensing method to find out that what portion on a given geometry has been deposited?
Okay, so so there are some sensors which is for thickness monitor, but generally, if it's a very small scale, it's quite difficult. But in most of the technology, we have the thin film deposition is called homogeneous deposition or conformal deposition. For example, plasma enhanced deposition technique always have the uniform deposition on the whole curved surface. It's only some technology like evaporation, thermal evaporation, which have the problem of the line of sight problem. But for other technology, you can solve it by just using plasma uniform designs. Yeah, I'm not sure whether another way is that if you really want to have deposit pattern, a different shape, you actually can using lithography make some sacrificial layer first, and then you deposit film. Well, after you release your sacrificial layer, you can have the pattern of the structure directly. Right. Okay.
Okay. Thank you.
Anybody else got any questions?
Hi, I was very fascinated, Nick Farmelo here, by the spiral electrodes and by the sensing work that you were talking about. but I wondered whether you collaborated with other people who use proteins on electrodes to be able to engender sensitivity to particular biomarkers, and whether you'd worked with people in biotechnologies around that area.
Yes, so we actually we have done quite a lot of work for the different biosensors. So basically, surface cold wave or cold wave method is one of the general sensing principle method. So it's the sensing, different type of sensing is depending on the pair of the sensing species. So if you normally we pre-coated with something, for example, antibody, then we can measure the antigen corresponding to enhance the selectivity. But in principle, is that the mechanism is the same. We can just try to find the best pair of the species to enhance the selectivity and also make the best device for enhance the sensitivity.
Thank you.
Yeah, thank you.
Great. I've got a question actually quickly to ask.
Hi, Harry.
Hi, how are you? Good to see you after a while.
Okay.
Yeah, I think it is so interesting. I mean, you've done extensively fantastic work. I mean, recently I can see this titanium nickel thing that you talked about for shape memory. Is it like a bimetallic strip structure, or are you talking something different?
So can you repeat again? So I just
the titanium nickel structure that you talked about as a shape memory, is it like a bimetallic strip, or is it like a composition of things that you have prepared?
So basically, this material itself is smart material. So that means if you control the composition, titanium nickel, the atomic percentage, you can get a very good shape memory itself. You don't need to use bimetallic.
That's the interesting part. But do you know that, are there any specific composition of titanium and nickel that you're adding here, or just they are?
Really depending on the temperature, operation temperature. You can control, so normally it's 50-50. But the 50-50, you get the transformation temperature is like a 70 degrees C or very large hysteresis temperature. But then we actually adding the copper and also other element inside. So you reduce the transformation temperature.
That's very interesting work, actually, Richard. I think I'll be in touch with you. Yeah.
Okay.
There are a few overlapping interests of mine coming in here. Okay. Are you part of NPAC in Northumbria? Where are you placed at the moment?
I'm in physics and electrical engineering. So we are actually in solar cell photovoltaics.
Yeah, because I know Ian Forbes.
Yeah, we are together. Yeah.
Nick, oh, are you together? Oh, wow.
Yes, Nicola.
Say my regards to them. Yeah.
Yeah. Okay. Thanks.
Oh, wonderful.
Yeah.
Okay. I'll let others to go. Okay, now I've got another meeting to go. Thank you.
Thank you.
See you later. Bye.
Bye.
Any more questions at all? You said that you deposited DLC as a means of controlling, using the residual stress within the DLC to control the bending. So how easy is it to control the stress in the DLC, and is it uniform?
So basically, depending on the methods, so some of the deposition method have very highly stressed. So for example, we actually using the arc coating method, so which is very thin layer, but is highly stressed. So, but if you're using the magnetron sputtering method, using the target of graphite, normally stress seems not as large. Or if you're using the PCVD, it's actually sometimes lower stress. So it's depending on the application. For this specific application, we're using the arc deposition, which is highly stressed.
Filtered arc. I guess filtered.
Yeah, a few filter arc. Yeah, sorry. Mhm.
Any other questions at all? It's not like Swarab not to have a question. Have you got a question, Swarab?
Sorry, he's left.
Oh,
He had to go for another meeting.
oh, okay. Well, I can assure you, if he hadn't had to leave, he would have had lots of questions. Well, how are we time-wise, Pamela? Are we coming up to our?
Yeah, we are already 1 o'clock.
Okay. Well, I guess people probably have got other meetings scheduled. So I really would like to thank you, Richard. That was really excellent talk. And we've got thumbs up from Nick, so all's good. And keep a watch out for emails from us, and we'll keep you informed as future webinars. And I'm sure that as a result of this, Richard, there's going to be a lot of follow-up interest with you on what you do.
I hope so. Yeah, to have more new collaborations. Yeah.
That's what we're here to encourage. That's what the network is here to do, is to try to get academics to work together. So that's perfect.
Yeah, thank you.
Thanks very much again, Richard.